Now, look at simple example number 6. A equals to x over y. Okay, x is variable and y is variable. So, this is division of variables. Okay, so to differentiate division of variables, we need to use quotient rule. Okay, so using quotient rule, okay, we differentiate A, it become A prime equals to, okay, we use quotient rule formula VU prime minus UV prime over V squared. Okay, we define U equals to X and we define V equals to Y. So when we differentiate X, we have 1, and when we differentiate Y, we have dy over dx. And after that, we substitute into quotient rule formula. So we substitute into VU prime, so we multiply V and U prime, so we have Y times 1, which is equals to Y. And then minus U times V prime, so we multiply X times dy over dx, so we get this, over V squared. Our V is Y, so we have Y squared. So this is derivative of X over Y using quotient rule, right? Okay, how about if we have A equals to 2 over Y? Okay, 2 is constant, okay, and Y is variable, right? So we don't need to use quotient rule, okay? We can move Y from denominator to numerator using properties of indices. So we have 2y the power of negative 1. If we put bracket here, we can compare with generalized power rule. Okay, so when we differentiate A, it becomes A prime. So we can differentiate 2 bracket y the power of negative 1 using generalized power rule. Okay, when we use generalized power rule, we move power to the front. We still have constant here in front, and then we multiply by the power, so we have negative 2 here. Then we copy in bracket and then power minus 1. So negative 1 minus 1. So we have negative 2 here. And then we differentiate in bracket. So we differentiate y. So it becomes dy over dx here. Right? And in between multiplication operation. And after that, we can write A prime equals to negative 2. We move y the power of negative 2 to denominator. So we have y squared here. So the answer when we differentiate A, we have A prime equals to negative 2 over y squared dy over dx. Okay, if A is constant over y. Right, just now variable over variable. Okay, so here constant over variable. Alright, so this is division between constant and variables. Okay, or we can differentiate this question using quotient rule. Okay, so when we use quotient rule, okay, we define u equals to numerator 2 and then we differentiate. Okay, and we define v equals to denominator y and then we differentiate. Alright. Okay, and then we use quotient rule formula A prime equals to VU prime minus UV prime over V squared. So we substitute into this formula. So we have A prime equals to Y times 0 is 0 minus U times V prime. So 2 times dy over dx here over V squared. Okay, V is Y. So over Y squared. And then when we simplify, so we have A prime equals to negative 2 over y squared dy over dx. So, it is equivalent when we differentiate using generalized power rule, right? So, it means that when we have division between constant and variable, we can use generalized power rule, okay? Alright, so this method is correct and this method also correct, right? For division between constant and variable. But for division of variables means that numerator is variable and denominator also variable, we need to use quotient rule only, right? And then number 7, okay, simple example number 7, b equals to sine 3y. Okay, so using trigonometric rule, because we have trigo here, okay, we differentiate b, it becomes b prime equals to cos 3y times 3 dy over dx. Okay, how we get this? Okay, when we differentiate sine 3y, okay, we will get cos 3y because we refer from the simple formula for sine single x. Okay, when we differentiate sine single x, so it becomes cos x. So when we differentiate sine 3y, it becomes cos 3y. But after that, we need to differentiate the inner function. So we differentiate inner function 3y. So we have 3 dy over dx. Alright. And after that, no more inner function. So we stop here. Okay. Then we can simplify. We just bring 3 dy over dx to front. So we have b prime equals to 3 dy over dx cos 3y. Right? Okay, next, number 8, c equals to cosec 3y squared. Okay, so using trigonometric rule, because we have trigo here, okay, we differentiate c, it becomes c prime. We differentiate cosec 3y squared, so it becomes negative cosec 3y squared cot 3y squared 6y dy over dx. Okay, let we look the step. Okay. Okay, when we differentiate cosec 3y squared, we can refer from derivative of cosec single x. Okay, it is equals to negative cosec single x cot single x. So now our single x is 3y squared. So when we differentiate cosec 3y squared, okay, we have negative cosec. We replace x now by 3y squared and then cot. And then we replace x by 3y squared. Alright. And then we differentiate the inner function 3y squared. So when we differentiate 3y squared, it becomes 6y and then dy over dx. Alright. And after that, okay, we can move 6y dy over dx to the front. So we have negative 6y dy over dx cosec 3y squared cot 3y squared. Right? Okay. And then number 9. D equals to e the power of 4y. Right? So this is exponential function. So using exponential rule, okay, we differentiate d, it becomes d prime. We differentiate e the power of y, the power of 4y. So we have e the power of 4y times 4 dy dx. Right? The steps are, okay, when we differentiate e the power of y, we can refer formula derivative of e the power of single x. And we get back e the power of single x. So means that when we differentiate e the power of 4x, we will get back e the power of, when we differentiate e the power of 4y, so we will get back e the power of 4y. But after that, we need to differentiate the exponent. So we differentiate 4y, so we have 4 dy dx. And then we just rearrange, so we can put 4 in front, so 4 e the power of 4y dy over dx. Alright? Okay, now look at number 10. Okay, if a equals to e the power of tangent y, okay, so we can differentiate using exponential rule combined with trigonometric rule. Alright? Okay, we differentiate a, the symbol should be a prime, and then we differentiate e the power of tangent y, so we have e the power of tangent y times sec squared y times dy over dx. Alright, first step, when we differentiate e the power of tangent y, we can refer derivative of e the power of single x, and we will get back e the power of single x. So, if we differentiate e the power of tangent y, we will get back e the power of tangent y. Okay, and after that, we differentiate tangent y. It becomes sec squared y. Okay, this comes from formula derivative of tangent single x equals to sec squared single x. So, when we differentiate tangent y, so it becomes, we replace x by y now, so it becomes sec squared y. Alright? And after that, we differentiate y with respect to x. So, we have dy over dx at the back. Alright? And then we just rearrange, so we can write a prime equals to sec squared y e the power of tangent y dy over dx. Alright? Okay, number 11. If we have b equals to ln to y, right? So, using logarithmic rule, okay, we differentiate b, it becomes b prime. We differentiate ln to y, so we have 1 over 2y times 2 dy dx. Alright? First step, when we differentiate ln to y, we can refer formula derivative of ln single x. And it is equals to 1 over x. Okay? So now our x is 2y. So when we differentiate ln to y, it becomes 1 over 2y. Okay? And after that, we differentiate to y. And it becomes 2 dy over dx. Alright? Okay, then we can simplify 2 and 2 from denominator here. And after that, our b prime equals to 1 over y dy over dx. Alright? Coming up next, examples of implicit differentiation. Thank you for watching. Stay tuned. Bye. Assalamualaikum.